and welcome to another video in the Fiddler.ai Explained series. In this video, I'm going to be following up on some of the ideas that my colleague Mary touched on in the previous video, basically which she introduced the concepts of algorithmic fairness and bias. In this video, I'll be talking about a paper that we published that takes the ideas that were discussed in the previous video and applies them intersectionally. So the paper that I am going to be talking about today is called Characterizing Intersectional Group Fairness with Worst Case Comparisons. I wrote this paper with my colleagues Lea and Mary at Fiddler, and this was accepted as a workshop paper at the AAAI Diversity Workshop in 2021. The full text PDF of this paper is freely available online, so I suggest you check it out. So, a brief overview of why fairness. So as Mary discussed in the previous video, and just for a refresher, machine learning systems are often biased due to a variety of complex causes like pre-existing societal biases, unbalanced training data. So say if your machine learning model has training data which is completely unbiased, like if you have a huge sample of a majority class and a very small sample of the minority class, research has shown that even like a simple algorithm like an empirical risk minimization model will somehow give higher penalties to the minority class. So it is important for us to build these notions of societal fairness into machine learning models. But then how do we do that? Social biases in algorithms are actually not as innocuous as people would think. One of the most famous examples in this field was a study by ProPublica where they showed that an algorithm that basically assigned risk scores seemed to assign higher risk scores to Black people, even though they actually didn't have that long or that violent of a criminal record. So these are issues that can have real impact on people's lives, and it is very important that we try and see what these algorithms are doing and how do we fix these biases. United States laws actually provide several kinds of protections for historically discriminated subgroups. So at least in the case of employment, the Equal Employment Opportunity Commission provides certain or defines certain protected categories which are listed on the screen. So they would be stuff like age, your race, your gender, also other things like your compensation, if you have, whether or not you have a disability, your genetic information, your national origin, your religion, and stuff like that. Additionally, all over the world, there are laws that basically deal with protected categories. So for example, in the European Union, you have GDPR, which provides privacy and protection laws. You have Canadian laws which provide protection for minorities. Under the Indian law, there are well-defined subgroups that are eligible for legal protection. So these issues are well known even outside of AI under legal jurisprudence. So now, given the status of fairness or machine learning fairness that has already been talked about in the previous video, now let's try and define what intersectional fairness is. So intersectionality is something which is defined along overlapping dimensions. So intersectional fairness thereby is similarly defined as fairness along overlapping dimensions, including race, gender, sexual orientation, etc. So essentially what I'm trying to say is that you might belong to a minority subgroup according to your gender, you might belong to a minority group according to your race, and when you combine these two things, you might belong to a minority subgroup that takes into account your race and gender. So these overlapping dimensions actually create more nuanced identity representations of people, and this is the concept we'll be taking further. So how does this impact traditional notions of fairness? To drill into this problem a little bit further, I will be discussing a problem which has been referred to as fairness gerrymandering. So in the image on the right, you see decisions made by an algorithm. The dark blue circles denote the individuals who have passed according to the algorithm, and the light blue circles denote the people who have failed. Now, if you observe carefully, you see that according to the algorithm, or according to the outputs of the algorithm, only black men or white women have passed. However, all white men and all black women have failed according to the algorithm. Now, if you took a traditional definition of algorithm, which basically tried to measure fairness along either the race axis or either the gender axis, basically non-intersectionally, something that we call marginal attributes in the paper, you would see, not surprisingly, that an equal number of men and women pass. So from the diagram you can see that 5 men and 5 women have passed, and also 5 white people and 5 black people have passed. But that completely hides the situations where these intersectional identities are treated disparately. So that's why this classification is still unfair, and that is the problem that we are trying to target with the intersectional definitions of fairness. So in this paper, we introduce a very simple framework to measure intersectional fairness, or to extend the definitions of classical fairness metrics that has been talked about extensively into a very simple disparity framework. So we use the Rawlsian principle of distributive justice. Essentially, what we do here is that we select a fairness metric, any metric that might be. So it could be equal opportunity, it could be, disparate treatment. And then what you do is you compute the fairness metric for each subgroup. So unlike traditional fairness definitions where you measure, the pass rate for each gender or the pass rate for each race, you calculate it for each subgroup. So you take the Cartesian product over all of your marginal attributes, and then you measure the pass rate, or you measure that fairness metric for each subgroup. So you measure the fairness metric for, say, black men, black women, white men, white women, if there were two genders and two races, for example. So this formulation represents the worst case disparity for any given algorithm, because if the minimum by maximum ratio is close to 1, that means all subgroups in between the worst treated subgroup and the best treated subgroup actually also fall within that bracket. So the idea here is to improve the condition of the worst treated subgroup, and therefore we call it the worst case disparity framework. So the idea, at least in this case, would be to try and add a constraint to your machine learning algorithm so that the min by max ratio is very close to 1. Now let's talk about some of the traditional fairness metrics and see how our framework helps to expand this and incorporate intersectional fairness. So first, let's take fair classification metrics. So one of the most used metrics is demographic parity, which basically says that each segment of a protected class should receive positive outcomes at equal rates. Essentially, it tries to compare the pass rate, basically the rate of positive outcome, of two groups. So traditional demographic parity is given in the first equation, where basically you are trying to say that the probability of passing, or the pass rate for subgroup 1 is equal to the pass rate of subgroup 2. We basically then transform it using our min-max ratio principle, or a worst case principle, and say that the demographic parity ratio would be the minimum value of the pass rate for a subgroup divided by the maximum value of the pass rate for some other subgroup. Essentially, say subgroup 1 has the lowest pass rate, and the subgroup 5 has the highest pass rate. So DPR here would be the ratio of these two numbers. And again, the ideal case would be if this ratio is very close to 1. If it is farther away from 1, that means the subgroup that is being treated the worst is actually has a very high value of disparity, far away from the group that is being treated the fairest. Another metric that is defined under US law is disparate impact. And here we measure, same thing, we measure the pass rates between two groups, but at least according to the law, we have to measure pass rate between only two subgroups. So essentially, how we expand this using our worst case disparity is that we take the pass rates between all two possible subgroups, which basically gives us the disparate impact ratios between all possible pairs of subgroups, and then we take the minimum of that value because that is the worst case ratio. The same principle can be extended to other fairness classification metrics. So in the paper we talk about demographic parity, disparate impact. We also talk about other metrics like group benefit, where again for the intersectional you take the ratio of the min and the max group benefit. And we talk about equal opportunity, which basically tries to achieve the same true positive rate per subgroup. The intersectional version of this would be the ratio of the minimum and maximum. There are also other classification metrics like false positive parity, true positive parity, which is equal opportunity, a false negative parity, true negative parity. So essentially all possible combinations of the confusion matrix. And all of them can be basically expanded in the worst case classification, or the worst case disparity ratio framework that we propose. So the next obvious question is that pass rate, etc., is defined for binary classification. How is our framework applicable for a case which is something like a multi-class classification? So like you don't have either 0, 1 output, you have a range of possible outputs or a range of possible classes. So we basically take that idea and expand it in the following way. So for each possible discrete output, so say your algorithm outputs one of three possible values. It can output either a 0 or a 1 or a 2. So for each possible output, so say we take all the subgroups whose outputs have been given as 0, and we find the min by max odds ratio for that possible subgroup. We do the same for output 1, we do the same for output 2. And then we take the minimum of the min-max ratio over all these values because that represents the worst case scenario. Once again, the ideal case is achieved when the minimum of the min-max ratios is equal to 1. That means every other value, every other possible combination has achieved parity. How would you solve this problem if you did not have output classes, but you had a continuous output, essentially like a probability output, which is very common, which is something like continuous outputs happen in cases like regression, or say you are training a model which outputs a number instead of a probabilistic number between 0 and 1 instead of the classes. Well, there are different metrics available in the literature which basically try and find the distance between two distributions, and so we leverage one of them, which is the Kale divergence between two distributions in the paper. Or you can use any distance metric between two distributions. We just show as an example the Kale divergence over here. So basically what we're proposing is that you find the Kale divergence between all possible pairs of subgroups. So for instance, the red line could be the output probabilities for black men. The blue line could be the output probabilities for white women. You find the Kale divergence, the distance between these two distributions, and the worst case scenario over your entire classification system or your entire regression model with the continuous output would be the max distance. So the maximum distance between any two pairs of subgroups would be the worst case Kale divergence, and that is what we would try to optimize. We would try to make the maximum distance equal to 0. What about ranking algorithms? Ranking or recommendation algorithms are used very commonly. You might have a search retrieval system. You might pass a query and your model might output a list of things that you want to see, or you might already have a list and you might want to re-rank it based on some objective that you're trying to achieve. How do we make these things fair? So there are a lot of fair ranking metrics as well. I will discuss two different ranking metrics from two different families. So the first kind of metric that I'm discussing is the representation based metric, which is called skew. So the skew for a subgroup is defined as the proportion of people from that subgroup in the top k divided by the proportion in the entire population. Essentially, Skew basically measures um, how uh, how more or less represented you are, or like a particular subgroup is in the top k, essentially. Say for example, in the top 10 of your ranking as compared to the entire population. um, for example, if there are 100 people and 50 of them are women, but when you take a top 10 ranking, only there are only 3 women, so then the skew is basically 3 by 10 divided by 50 by 100, which is 0.6. So a skew of 1 is obviously ideal because that shows that there is no disparity in the top 10 in the overall population. Here, very simply, what we did in the previous discussion, the worst case disparity, or the worst case disparity in the representational case, basically the skew ratio at rank k, would be the minimum skew over all subgroups divided by the maximum skew over all subgroups. And again, once again, we want this min by max ratio to be 1, which shows that like no group is particularly skewed as compared to others. The second class of ranking metrics we discuss are exposure family of metrics. So essentially the attention. So like we have, so this is a screenshot from a paper by Sapizinski et al. From Northeastern, and basically what it is trying to show that your visual attention when you look at a ranked list basically goes down from the top to the bottom, and basically people who are at the top of a ranked list get the most visual attention. So like, measuring the attention over the ranking list for each subgroup is another fairness metric, or rather another ranking metric. And a fair ranking essentially will try to provide equal exposure to people belonging to all subgroups. So here, exposure can be measured as the average attention per subgroup. So essentially you take all the black women, for example, in your list, and you add the attentions or the exposures each of them have received, and then you average it out over you divide this value by the number of black women in your data set, and that gives you the average exposure for the subgroup equal to black women, and so on and so forth. And the worst case disparity again would be the minimum average attention for overall subgroups divided by the maximum average attention, and again we want this attention ratio to be equal to 1. Finally, to wrap up our discussion and to show how applicable our worst case framework is in a real life scenario, we basically take a pre-trained model on the dataset, which is the law school's admissions dataset. We basically took a pre-trained TensorFlow model from Google's website, and the link is available in the paper. And we basically look at the false negative rates over all the subgroups. So if you look carefully at the graph, you will see that, for instance, when you only look at race, you see that white and non-white people have different false negative rates. Non-white people have slightly more false negative rates, which is a bad thing, because higher false negative rates would basically mean that a candidate who was actually eligible for getting into law school was falsely classified as negative or a failure. Similarly, when we look at binary gender, so when we look at men and women, we again see that men have a higher false negative rate than women. But when we look at this entire picture intersectionally, the picture is actually a lot more different. So for instance, we basically claim when we only look at binary gender that men always have a higher false negative rate than women, but that is not always true. When you look at this intersectionally, you see that black women actually have a much worse false negative rate than, say, someone who is a white male. So this is a real life example on a real life trained data set, which shows that intersectional depictions of metrics actually reveal a lot more about how your model is performing on different subgroups, that just looking at higher level marginal categories would not suffice. So how we apply our framework to this problem is again very simple. We basically take the ratio in the intersectional case between the race with the lowest false negative rate and the highest false negative rate, and we find the min-max ratio. We see that this ratio is 0.036, which is very far from the ideal value of 1. Now, and we don't show this in the paper, but if you were designing this algorithm, if you were writing the classification algorithm, you would essentially add, this is one of the many ways to solve this problem, but one suggested way is to add interventions using constraints during your training stage itself. So if you were trying to write a fair classification algorithm, you would add an additional constraint during your training step, which would measure this intersectional min-max ratio for false negatives and add that as a constraint. So your model would have to fulfill that constraint while learning. So ultimately, we would expect after this constraint machine learning has taken place that the output would be more fair and have somewhat equal false negative rates over all subgroups. So in conclusion, we basically propose a simple framework to extend conventional fairness metrics to incorporate intersectionality, and basically through this very simple and easy to understand framework, we basically condense the value as a single worst case measure, which you can then optimize for. So it basically packs in a lot of information into one number. And we have deployed this framework internally in our fairness monitoring system at Fiddler. So if you're using the Fiddler's fairness measuring system or fairness monitoring system, you would basically get access to these intersectional fairness metrics. There are obviously some limitations to using this very simple depiction or this very simple framework. So for example, this does not help you to measure continuous features. So if your feature itself was not possible to bucket into subgroups for, say, something like age, which is actually a number and not groups, you would have to create groups by bucketing them. And also there might be certain subgroups which are hard to define. For example, for at least this case study, we have considered gender as a binary men versus women, but there might be people who might not, identify as belonging to either of these buckets. And because gender or gender identity is considered as a spectrum, it is essentially a feature. It is essentially a subgroup that is hard to define, and it's continuous and it's like a spectrum. So we are conducting research on trying to incorporate intersectional fairness metrics that try and take into account these issues. And essentially that concludes this talk. Thank you so much for joining.